Welcome to the second session on HSFG boards. In this session, we'll be taking up the problem on design of joint using HSFG boards. So the problem statement is over here. An ISA 100 by 100 by 10 carries a load of 220 kilonewton. It has to be connected to a gusset plate of 12 mm thickness using HSFG boards of 16 mm diameter and with the property class of 8.8. Two cases which have been mentioned are: one is no slip is permitted, the second when slip is permitted. Grade of steel is Fe410. So to begin with the solution, this is the figure showing the angle section which is carrying a load of 220 kilonewton, and this is the gusset plate, and the arrangement of bolt has been shown over here in a single row. So the load what is mentioned here is 220 kilonewton, and it is not mentioned whether it is under service condition or under ultimate load. So it has been assumed that the given load is a factor load or the ultimate load. The diameter of bolts what is given to us is 16 mm, and the diameter of bolt hole comes out to be 18 mm. So if you see in this table 19 of IS 800, so you'll find that for bolts of 16 to 20 mm diameter, the standard clearance required is 2 mm, and with that 2 mm standard clearance, the bolt hole diameter will come out to 18 mm, 16 plus 2, 18. The minimum pitch distance what has to be provided is 2.5D, so it comes out to be 40 mm, that is 2.5 times the diameter of bolt, it will be 40 mm. Minimum edge and end distances, so they are either 1.5 D naught or 1.7 D naught, depending on whether the holes are drilled using machine or they have been punched or in the plate. So with the assumption that we are having punched holes with help of die, this 1.7 D naught has been adopted here. So the minimum edge and end distances what we require is 30.6, 1.7 times the diameter of bolt hole, that will come out to 30.6. And we'll fix up the pitch distance as 45 mm, and edge and end distances will be 35 mm, which will be provided in the joint actually. So with these details of the connection, let us go with the first case, that is when no slip is permitted. So in that case, first is what is the design strength of friction grip boards. So it is expressed as VNSF upon gamma MF, and VNSF stands for the nominal shear strength of the friction grip boards, which is given by mu f into Ne into Kh into F naught. So mu f stands for the coefficient of friction between the two plates, and in this problem the data about the surfaces is not mentioned to us. We don't have any thing given about the surface condition of the two plates, gusset plate as well as the angle section. So we'll go for assuming that mu f value. So in case we don't have any data, we'll go for assuming the maximum value of mu f. The maximum value of mu f which is permitted is 0.55. So mu f can be taken less than this also, but it cannot exceed this 0.55. So I have taken the maximum value of mu f here, 0.55. Ne is the number of planes which are offering the frictional resistance. So these are the two members what have been connected, and in cross section you can see this is the gusset plate over here and this is the angle section. This is the only plane which is offering the frictional resistance for in this case. So Ne will be 1, since only one plane is there which is offering the frictional resistance. So Ne will be 1. Kh will be the factor depending on the bolt hole diameter. So for standard clearance, bolt hole with standard clearance, what we have taken here, Kh value is 1.0. So that is the Kh. Now coming to F naught, the force in the bolt, it has to be calculated. So F naught is dependent on the net area and the proof stress. For 16 mm diameter bolts, net area will be 0.78 times the gross area. So 0.78 into pi by 4 into 16 square. So that comes out as 156.8 mm square. And F naught is the proof stress, which codes says that it is to be taken as zero point 0.7 times the ultimate tensile strength. Grade of this bolt is 8.8, meaning its ultimate tensile strength will be 800 Newton per mm square. So 0.7 times 800, it is 560 Newton per mm square. So 156 into 560, this will be the F naught value. So altogether, the nominal shear capacity of the friction grip bolt, it comes out to be 48.29 into 10 raised to 3 newtons. When taken to the design shear capacity, the gamma mf value, factor of safety, what has to be taken is 1.25, because the load what we have assumed here is the factor or the ultimate load. In case you are designing the slip resistance at ultimate load, the factor of safety should be considered as 1.25. So dividing this nominal shear capacity of the friction grip bolt with this factor of safety, the design shear capacity of that friction grip bolts will be 38.632 kilonewtons. To find out how many bolts are required, it will be total load divided by the strength of each bolt. So 220 upon 38.632, that gives us as 5.6. So we'll round it off and provide 6 bolts with a pitch of 45 mm. So 6 bolts and the pitch distance will be 45 mm over here, and the edge distance what you need to maintain is 35 mm as we have decided earlier here. Okay, so this is the first case what we have when slip is not permitted. Coming to the second case, what is the second case here is slip is permitted. So if at all a slip occurs in this joint, okay, if this member is permitted to slip, if there is a relative motion or slip between these two members, in that case what happens is these bolts will no longer transfer the load through frictional resistance. Instead, they will start behaving as ordinary bearing type of bolts. So in that case, you need to find out what is the design design strength of these bolts. So design shear capacity of these bolts, that is bearing type of bolts. Now they are behaving as a bearing type of bolts. So their design shear capacity VDSB, which will be equal to VNSB upon gamma MB, and VNSB will be equal to FU by root 3 into NN ANB plus NS ASB. So FU, what we have here is 800 Newton per mm square. Okay, the strength will remain same, 800 Newton per mm square, because the property class of these bolts is 8.8. Ultimate tensile strength will be 800 Newton per mm square. So 800 by root 3 into number of shearing planes. Assuming that the shearing plane are lying in the threaded region, number of shearing plane will be 1 due to the connection what we have here. So we'll come across only one shearing plane, that is at the interface of these two members, gusset plate and the angle. So N will become 1, and A and B as calculated earlier, it is 156.8, that is 0.78 times the gross area, 156.8. So this will give us the nominal shear capacity as 72.42 into 10 raised to 3 newtons. Okay, and dividing that by factor of safety, VDSB, okay, it comes out to be 72.42 divided by 1.25, so it is 57.93. Factor of safety for the materials, you'll find it in table number 5 of IS 800. So for bolts it is 1.25, and this is one strength what we have based on the shearing resistance of the bolt. So in case of bearing type of bolts, what you find is bolts may either be transferring load through shearing resistance or maybe through bearing resistance. So calculating the bearing capacity of these boards, that is VDPB, which is VNPB upon gamma MB, and VNPB is given by 2.5 kb dt into fu. Okay, so these two parts what I am dealing with here, these we have already dealt in ordinary black boards or bearing type of boards, these two clauses, that is 10.3. so I have not mentioned anything over here, and you can refer IS 800, and you'll find that these two expressions are related to ordinary black boards. Okay, so 2.5 kbd into t into fu, and kb based on these parameters, e upon 3d naught, p by 3d naught minus 0.25, fub upon fu, or at the max it can be equal to 1.0. So out of these, the least one is 0.583. This is the least value of kb what we have, so this has to be adopted, 0.583. Okay, so 2.5 into 0.583, d the diameter of the bolt, t thickness of the thinnest member, that is 10 mm, the angle thickness is 10 mm, whereas the gusset plate is of 12 mm thickness, so t will be 10 mm. fu, the ultimate tensile strength of the plate, so that will be 410. Okay, so this fu is taken for plate because that is the member which is going to fail under bearing, since it is having the lesser ultimate tensile strength compared to the bolt, so 410. And what that gives us is the nominal bearing capacity as 95.61 into 10 raised to 3 newtons, and the design bearing capacity comes out to be 76.48 kilonewton. Out of these two, if you compare the shear capacity and the bearing capacity, the shear capacity is 57, so this will be treated as the strength of the bolt. So design strength of the bolt will be 57.93 kilonewtons, and number of bolts required in this case comes out to be 3.7, that is 225, the strength of the bolt, and it is 3.7, and we are going to adopt 4 bolts at a pitch of 45 mm. So these are the two cases in which we saw how we can design the connection using high strength friction grip bolts. First case required that the slip is not permitted. Second case, when slip is permitted. Thank you. So this is one more problem on HSFG boards in the second session, and in this problem you need to investigate whether this joint is safe or no. So the connection has been shown in this figure over here, and it has been asked to investigate the safety of the slip critical connection. The angle sections are connected with a bolt of 20 mm diameter, and they are high strength friction grip bolts of property class 8.8, and gusset plate thickness is given as 10 mm, and steel is of Fe410 grade. So the load what this angle section is carrying is 425 kilonewton factored load. Actually there are two angle sections which are connected back to back, which is clear in this cross section figure, and the bolt hole diameter, so it will be 20 plus 2 mm clearance, so 22 mm will be the bolt hole diameter. And since it has to be designed as a slip critical connection, that is slip will not be allowed, and the design strength of HSFG boards under such a circumstance will be given by the frictional resistance that is offered by the interface. So VDSF, design shear capacity of the friction grip boards, PNSF upon gamma MF, and PNSF, which is equal to mu f Ne kh into f naught, and mu f value what has been taken is 0.55, the maximum value of mu f. If at all if it is mentioned mu f, what is the value of mu f, adopt that, or else you just take it the maximum value of mu f, which is 0.55, and any number of shearing planes. That is what the difference here is. You'll find that in this case there are two planes which are offering the shearing resistance. The two angles have been connected to this gusset plates back to back. So there will be a frictional resistance experienced by these two interfaces. Okay, this is one plane which will be experiencing the friction, and one more plane on this angle and gusset plate interface. So two planes are offering the frictional resistance. For that purpose, Ne comes out to be 2. Kh for bolts with standard clearance, it is 1.0, and F naught, that is the force in the bolt, which is the net area of the bolt into the proof stress. The net area for 20 diameter bolts, it will be 0.78 times the gross area, and if you calculate, you will find that it comes out to be 245.04 mm square, and F naught 0.7 times the FUB, which is 560 Newton per mm square. So the nominal shear resistance will be 150.94 into 10 raised to 3 newtons. And what force we are dealing with is the ultimate force or the factored force. So factor of safety, what has to be considered is 1.25. So design shear capacity will be 120.752 kilonewtons. So this will be the strength of the bolt, HSFG bolt. And we'll find that in this connection, there are totally 6 bolts. Okay, so 6 into strength of each bolt, it will be 724.512 kilonewton. So that is more than the applied force, 425 kilonewton, and hence you can say that the joint is safe. So we have come across another condition wherein the shearing planes have increased. This is how actually the shearing planes may increase, okay, under such cases. So you need to identify what number of shearing planes are involved in that joint, which are offering the frictional resistance in this.